So in this video we're going to introduce the idea of relative extrema in the context of functions of two variables. And to get at this, we're going to look back at our definition of relative extrema for functions of a single variable and then kind of extend the concept into three-dimensional space. So in Calc 1 we said let f of x be a function that's defined over some open interval I, where the open interval I contains a. And then what we said is that if f of a is greater than or equal to f of x for every x on the interval I, then we called f of a relative maximum. And if it should be one if f of a was less than or equal to f of x for all x on the open interval I, then we said f of a was a local minimum at a. So essentially what we did is we said, hey, here's my function, and there's a y and an x-axis, and our domain lives on the x-axis when we're working with a function of a single variable. So we said, if we can find an open interval I such that there's a number a on that interval I where f of a is greater than or equal to all the f of x for every x in that open interval, then we said we had a local maximum. And if we were able to find an open interval, let's call it I sub 2, such that for all x in that open interval we could find a value a so that f of a was less than or equal to all f of x for x in that open interval, then we said we had a local minimum. So we used open intervals in our definition precisely because intervals are components of a line. All right, our domain, our input values live on a line, so we define things in terms of open intervals. And the problem is when we extend the idea into functions of two variables, our functions now are graphed in three-dimensional space. So our domain is actually a region R in the xy plane. So now instead of an open interval, what we're going to do is we're going to define relative minima and maxima in terms of an open disk R in the xy plane. So we're going to say, hey, if we can find an open disk that contains the point AB, and if for all the other ordered pairs xy in that open disk, if f of AB is greater than or equal to all of the f of xy's above that open disk, then we have a relative maximum. And if f of AB is less than or equal to all of the f of xy's for all ordered pairs in that open disk, then we have a relative minimum. So just graphically thinking about it, we're saying, hey, we're going to have a relative minimum if we can find a point right here, f of AB, so that if we can establish an open disk in the xy plane, f of AB is less than or equal to all of the f of xy's for every xy in that open disk, or if we can find an ordered pair AB so that f of AB is greater than or equal to all of the f of xy's in an open disk in the xy plane, then we say that we have a relative maximum. So kind of the same concept, just that we did in Calc 1, just extended into three-dimensional space. And then in Calc 1, when we tried to find relative maxima or relative minima, we needed to find critical numbers. So what we want to do is remember how we define critical numbers in Calc 1. So we said, hey, if we have a function defined at a and we discover that f prime of a is equal to 0, or if f prime of a is undefined or doesn't exist at a, then this should be a, then a is a critical number of f of x. And the key was that local minima or local maxima, so our relative or local minima and maxima only occur at critical numbers. So to find to find places where there might be relative minima or maxima, we needed to look for the critical numbers of the function. And the idea was, hey, if the derivative is equal to 0, you may have a point that locally over some open interval is a maximum, or you may have a point that locally over some open interval that you define is a minimum on the function. But if the derivative was undefined, then that could correspond to a sharp cusp or point in the graph that is a max or min, but at which the derivative's not actually defined. So we also needed to look for those places where our derivatives didn't exist. So what's going to happen then in three-dimensional space, where we're defining things over an open disk in the xy plane, we have to pay attention to the partial derivatives. And what we check, we're going to find critical points, not numbers, because our critical points are going to be ordered pairs AB. And we're looking for ordered pairs AB at which the partial derivative with respect to x and the partial derivative with respect to y are simultaneously 0. And those could be places on the graph that may correspond to a local minimum or maxima. So for example here, what you notice is that if I have a maximum what you notice here is that I do have a maximum right here, but the tangent line with respect to the x-axis is 0 right there, but the tangent line at that point with respect to the y-axis is also 0. So these hilltops or valley bottoms like this will correspond to places where the x and the y derivatives are simultaneously 0. But we still have to pay attention to places where the partial derivatives are undefined, because those could correspond to cusp in three-dimensional space that do themselves represent either a maximum or minimum value. So undefined partial derivatives, those are places where our partial derivatives don't exist. Those are going to correspond possibly to cusp, or looking for those partial derivatives equal to 0 could correspond to nice smooth mountain tops or valley bottoms. So those are the critical numbers, and the key is that once you found the critical numbers, those are the only places. Just like for single variable functions, the critical numbers are the only places at which relative minima or maxima might occur.